All right, so continuing with our function review. In the last one, we looked at linear and quadratic functions, and I mentioned at the end that these are instances, examples of a larger class of functions called polynomials. So let's just define polynomials and talk about a few of their properties. Again, I want to keep reminding everyone of this. This is meant to be a review for people who have already had experience with polynomials, but maybe need a quick brush up to get themselves reoriented on the topic. So a polynomial is a function of the following form. F of x is an x to the n, a sub n minus 1, x to the n minus 1, and on and on and on to a1x plus a naught. So in this construction, let's say what each of these things are. N is an integer, and then n is also going to be greater than or equal to 0. A sub n is a constant not equal to 0. Let's do this in a different order. All the a sub anything, so I'll call them the a sub i's, are real numbers, right? So constants, with the restriction that a sub n is not equal to 0, except in the case when n equals 0. Okay, so just let's clarify exactly what I mean by this. All we are saying here is that we have functions of the form, let's give an example, f of x equals negative 7x to the 9th plus 3x to the 8th minus 4x to the 7th minus x to the 6th plus x to the 5th minus 5x to the 4th plus 3x cubed minus 3x squared plus 2x plus 1, for instance. That's one example of a polynomial, okay, right? So in this case, this is the case where n equals 9. So this negative 7 is a sub 9. The 3 is a sub 8. The negative 4 is a sub 7. On down to 1 is our a naught. Okay, so each of those numbers in front, those are our constants. They're all real numbers, right? We don't write the 1 here, but there's a negative 1 there. There's a positive 1 here, negative 5, a 3, a negative 3, a 2, and a 1, right? So those are the a sub i's in that instance. This is the case where n equals 9. Let's do another example. So we have the restriction that a sub n is not 0, but it doesn't mean the other ones can't be. So for instance, here's another example. Let's go with starting with n equals 10, 2x to the 10th minus 1, right? This is the case where a sub 10 is the number 2, then a sub 9, a sub 8, and on and on and on. These are all equal to 0. Right? All the rest are 0, except for at the end, we get a naught equal to 1, right? So all these ones in the interior, right? The dot, dot, dot just means we keep going down all the way until we get down to 1 and then 0. All those, any combination of them can be 0, right? Let's do another example. H of x equals 3x to the 5th plus 2x squared minus x, right? Here's a case where n equals 5, but the n equals 4 and 3 and 0 constants are all 0, right? Where the other ones we have a sub 5 is 3, a sub 2 is 2, and a sub 1 is negative 1. Okay. The only exception where n can be equal to 0 is the case where n equals 0. That is the case where we're looking at when n equals 0, right? We only have one term, this constant term, right? So this is like a constant function, like k of x equals 7, right? And in this case, we allow that we can have a 0 there. We could have the constant function m of x equals 0, the 0 function, right? It's not a very interesting function, but it's allowed. The reason we don't let any a sub n be 0 otherwise is then we don't have this first term. The next term would be our highest term. We're always looking for what is the highest power in this polynomial. If this first one's 0, well, that one's not, there's no point in writing that one there. We would start with the next one. So we just throw that out. We like to know what the highest one is, right? Notice I'm always writing these from highest power to lowest. There's no rule that says you have to, but it's convenient because that highest power tells us a lot about the polynomial. We call the highest power, in this case, what I've labeled n, we call n the degree of the polynomial, right? So that's just a piece of vocabulary. It's nice to know what the degree of a polynomial is. What is the power, its highest power, okay? So let's look at, we already mentioned that when we were talking about linear and quadratic functions, that these are examples of polynomials. So let's just see how that's true. So let's start with the case of when n equals 0, we have functions that look like f of x equals some constant, and these are just constant functions, right? These are all just going to be a horizontal line at some level. When we increase n to 1, we will get things that look like a1x plus a0. And these are our linear functions, right? When we talked about, when we typically talk about linear functions, we label the coefficient of x as an m and this constant as b, right? mx plus b, doesn't matter. I'm just now using the notation of polynomials. All that we care about is we've got a constant next to a single power of x, and then a constant by itself, and this is our linear functions, right? In this case, a1 is the slope and a0 is the intercept. When we increase to n equals 2, we get a2x squared plus a1x plus a0, and these are our quadratic functions. Right, so again, we recognize this as the same form as what we looked at last time. Let's just do one more. N equals 3. All right, cubic functions, a cubed x cubed plus a2x squared plus a1x plus a0. These are our cubic functions. And we can keep going. There's names for many of these. But it's easier at some point just to say it's a degree 3 polynomial. Maybe after cubic, people typically start saying it's a degree 4 polynomial, degree 5, degree 6, unless you're working with them all the time and have all those names in your head. This is where most people probably stop using these special names. All right. So one thing to notice, I mentioned earlier that we often care a lot about the degree of a polynomial. And one reason for that is that the degree tells us a lot about how a function behaves. So let's look a little more deeply at that by noting that polynomials are built, oops, missed an L in there. That's nice. Polynomials are built out of what are referred to power functions, right? These are just things of this form, ax to the b, a constant times x to a power that's an integer, right? So here b is the b is a positive or non-negative integer. These are power functions, right? So each little piece of our polynomial, this little piece is a power function, a constant times x cubed, a constant times x squared, a constant times x. right? These are little power functions, and we sum them together, right? Polynomials are sums of power functions. And if we look at the power function, that's the degree of our polynomial. In other words, we look at the power function with the highest power, right? So we look at this first little piece of each polynomial. The power function, let's say it this way, of degree n in the polynomial gives us the end behavior of the polynomial itself. I know this might not mean much at this moment. We'll get there. So let's pick this apart. Let's actually start at the end, what we mean by the end behavior. So this is a nebulous term a little bit. It's maybe nebulous is the wrong word. It's just a little bit difficult to define at this point. The end behavior is what happens as x gets very far from 0, right? In other words, if we make x really, really big or really, really big in the negative direction. I don't like to say small in the negative directions because they're still big numbers. It's just in the opposite direction. Small kind of implies things close to 0. So if you think of x on a number line, 0's in the middle, we're looking what happens as x gets very far away from 0. A good question about this is, what does very far mean? Well, maybe the easiest way to think about that right now is that very far just means past the place where there's any surprises, where its behavior settles down and it just keeps doing the same thing. And we'll show some examples of what I mean by that in a minute, right? So very far can be x equals 10 and larger, or x equals 1 billion and larger. It depends on the function, but we just mean that the function itself starts to calm down and settle into one sort of pattern at that point, right? So when we look at the power function, what we're going to find is that if we look at a cubic, for instance, and we look at the cubic, if we look at this cubic and this one that has these other 3 terms, they're going to have the same end behavior. Those 3 lower terms don't do much. So let's stop talking about it and show some examples. So let's go to the graph. Let's start with quadratic functions. So here's the simplest power function, x squared. Simplest quadratic power function, x squared, right? And here's another quadratic function that begins with x squared, and then it has this minus 4x plus 2. Right, and so if we look at these 2 graphs, let's clean this up a little bit. All right, we probably don't need any grid at all. If we look at these 2 functions, they're not very similar, right? This red one never becomes negative. We can see that they're, if we evaluate, for instance, at 2, the green one is way down here, the red one somewhere up here, right? There's a big difference between them. There's some similarities to their shape, but they're not all that similar. However, if we begin to zoom out, let's do, oops. So now on the Y. So if you notice the scale here, right? So x is now going out past 400, almost to 600, it looks like, and our scale is going up to 250,000. We can still see a very slight difference between these 2 graphs, but not very much, right? That all that difference that we saw, one was below the x-axis, at this scale, zoomed way back, those differences don't amount to much, right? And so the difference between these 2 functions out at 400, right? If we put in the line x equals 400, these two functions intersect that line fairly close together, right? Their difference is less than 2,000, which is a big difference, but not when you think of it relative to how large the value is. 2,000 out of 160,000 is not that big of a difference, right? So this end behavior, and I can keep zooming out and seeing how closely aligned they become. They're almost the same function. Right, so that starts to give us an idea of what I mean by this end behavior and how it's determined by that power function at the beginning. Right, all these differences that happen near zero don't amount to much. All right, let's do the same thing for a cubic. So here's x cubed, a sort of classic cubic function. The classic cubic function. And let's look at this one, x cubed minus 7x plus 3, right? Wildly different functions, right? They have very different graphs here. Let's change the colors so they're very much easier to see, especially when we zoom out. Right, this orange one has this peak and then this valley that the purple one doesn't have at all. So here we are near zero. They don't seem very similar at all, but let's do the same thing. Oops. Let's make this. But as I zoom out, and I haven't zoomed out nearly as far as the other one, we already see how much similarity we see between these two, right? That massive hump, that massive peak that the orange one had and massive valley at this scale don't look like such a big deal. Things are very similar between these two functions. And as if I zoom out more, we see that they look even more similar, right? So this end behavior, let's go back and compare end behaviors. Remember what I said, what happens as x gets very, very far from zero. So in this cubic function, looking at this, right, regardless of what we have, so right, for both of these, as x gets larger, so one way we can say this, as x goes to infinity, right? Keeping in mind, infinity is not a place we can go to, it's the way we say it, just meaning as x gets larger and larger, x cubed also goes to infinity, right? So if you look at this graph, as I keep moving right, the graph gets increasingly hard for both of these. All that stuff near zero doesn't matter. And as x gets large in the other direction, as it goes to negative infinity, x cubed also goes to negative infinity, right? Let's go back to the quadratic, right? Here, so we have y equals x squared and y equals x squared minus 4x plus 2. These have the same end behavior as well. As x goes to infinity, x squared, or let's just say it as y, also goes to infinity. In this case, as x goes to negative infinity, because of that squaring, we still go to infinity, right? On both sides of this graph, as x gets larger and larger, y gets larger and larger, okay? And this is what we mean by the end behavior, right? And it wouldn't matter if we threw, for instance, a positive constant in front of this, right? It gets bigger faster, right? When I put a 2 in front of there, but they're both still going up. What will matter is if I put a negative constant in front of this, right? And when I say it doesn't matter, what I mean is it obviously changes the function. Totally different things are happening, but it doesn't change the end behavior. Multiplying it by 2 or 2,000, this thing's still getting larger as we go in the positive and negative values for x. On the other hand, if we throw a negative constant, for instance, -1, that end behavior reverses. As x goes to positive or negative infinity, the output values go to negative infinity, right? As opposed to, in this case, with the positive leading coefficient, right? That coefficient at the front of the polynomial, at the highest power, at the degree and term. When it was positive, we were always going to positive infinity. When we make it negative, that flips and the outputs go to negative infinity. So let's do the same thing for a cubic. So again, here we have the two that we looked at. To the right, it gets positive. To the left, it gets negative. Nothing would change even if I multiply this by, let's say, a positive 1/10. Right? They're still doing that. They're just getting there a little bit slower, right? On the other hand, if I multiply by negative, in this case, a -1, we see it flip. Now, as x gets increasingly negative, as we move to the left on this graph, the output values are going to positive infinity, and as we move to the right, they're going to negative infinity. So we flipped that graph over, right? So the end behavior of these functions is completely determined by that power function at the front, right? So in this case here, this power function 0.1x cubed, if we understand the end behavior of it, we understand the end behavior of the whole polynomial that begins with that, right? This is our leading term, the term with the degree n power in it, right? And so if we have a polynomial with negative x cubed at the beginning, we know that it goes off to negative infinity as we make x more negative, and it goes to positive infinity as we make x more negative, and it goes to negative infinity as we make x more positive, looking at this graph, right? So what about higher powers? Well, what's nice is that x squared and x cubed really tell us everything we need to know. Because as I make higher powers, here's x squared, here's x to the 4th, here's x to the 6th, here's x to the 8th. They're doing the same thing, right? Again, we're only looking at big behaviors. Let me zoom in a little bit here. Right, that even though, yes, the x to the 4th or x to the 8th goes higher much quicker, it's flatter towards 0, but then all of a sudden shoots up much more, it's still curved upwards in the same way. So if I have a polynomial like f of x equals 9x to the 10th minus 2x to the 5th plus x cubed minus 3x squared plus 200, and I ask about the end behavior, all I need to think about is y equals 9x to the 10th. And the graph of this, because x to the 10th, right? So I stopped at the 8th here, but we keep going. They all look this way. These even powers all look the same. I know that this thing is going to look like this. And so as x goes to plus or minus infinity, f of x goes to infinity, right? In other words, it doesn't matter which direction, which values of x we start putting in as we go further and further away from 0, f is just going to keep getting bigger, right? And we can tell all of that just by looking at this first term, right? What really happens is all these other terms, as x gets larger and larger, matter less and less, right? Let's do a quick example of that. If I had the function g of x equals, let's just make it x to the 10th minus x, right? I'm doing a simple example just to kind of get the idea across. If we take g of 1, well, 1 to the 10th minus 1 is 0, right? That minus x mattered a lot. But as g gets bigger, let's say 10, then we're doing 10 to the 10th minus 10, right? What does 10 to the 10th look like? I hope I counted the zeros correctly, something like that. But if you look at this number, this is approximately the same as 10 to the 10th, right? If you're talking about something with this many zeros after it, right? What's the difference between 1,000,000,000 and 999,999,990, right? If you take 1,000,000,000 and subtract 10, no one would care if they got $1 billion or 999,999,990, right? We would think of that as the same amount of money. The difference between those $10 when you got $1 billion is so inconsequential, and that's essentially what happens here. So even though the function has this x that matters when x is small, as soon as x gets big, it barely tells us anything about what's happening to the function, and that leading term really dominates. It doesn't matter if this next term is x to the 9th. It takes longer for it to matter, but what's the difference between 1,000,000,000 to the 10th and 1,000,000,000 to the 9th? 1,000,000,000 to the 10th is 1,000,000,000 times bigger than 1,000,000,000 to the 9th. So it is, even though they're both massive numbers, one is massively more massive than the other one, okay? Okay, so let's keep going. So there's the higher powered even ones. We get the same sort of thing with our odd functions. Here's x cubed, right? You can see both of these, even though the linear one doesn't quite have all those curves, it's still getting larger in the positive direction and more negative in the negative direction, as is the x cubed and the x to the, and the x to the 5th and the x to the 7th, right? They're all doing the same thing. And if we throw negatives in front of them, right, they all get flipped the same way. And so the end behavior cases we talked about here are all the end behavior cases, right? So we have all these different things, and then plus the flipped cases, right? So these are two where we have positives in front, and then if you have negatives in front, we have these flipped cases. And so those are all the things that can happen with polynomials in terms of end behavior, okay? However, end behavior isn't the whole story. When we're thinking of large x's, we don't care much about what happens close to 0, but sometimes we do. Sometimes we care a lot about what happens close to 0, because maybe what we're using this for doesn't really have anything to do with super large values of x. So let's talk about another feature. This is a feature that we think of as happening more close to 0. Let's talk about the intercepts of polynomials. Okay. So let's start with the easy one, right? Let me write the definition of a polynomial again. We have f of x equals an to the times x to the n plus a sub n minus 1, x to the n minus 1, on down to a sub 1x plus a naught. There's the form of the polynomial. Now, let's start with the easy part, the y-intercept. Right. This is true for every function. If any function has a y-intercept, we find it by evaluating the function at 0. So in the case of a polynomial, that means we just get the constant term, because all those x terms get wiped out by that 0, which means our intercept happens at 0, a naught, right? Just whatever that constant term is, that's where we intercept the y-axis, okay? Much more difficult, typically, is the x-intercept, right? The x-intercepts, I should say, there might be only one, but there could be more than one, depending on the kind of polynomial we have and what those constants are. These are all the x values solving, or let's say such that f of x equals 0, right? So where are the places on the graph where the y coordinate is 0? In other words, it's touching the x-axis, right? Solving this equation can be difficult, right? So let's go through a couple of our kinds of polynomials, right? If we have a linear polynomial, f of x equals a1x plus a naught, we're simply solving where is this equal to 0, right? So we just need to solve this equation. This one we can do in our heads. This is going to give us x is equal to negative a naught divided by a1. Remember, we insist that a1 is not 0 for this to be a linear polynomial, so dividing by that a1 is fine. And our intercept will be the point negative a naught over a1, 0, right? So for example, if our function is f of x equals 3x minus 19, and we want to know where this is, it hits the y-axis, the x-axis, we simply solve this equation and we get 19, whoops, and x equals 19 thirds, right? So the intercept is 19 thirds, comma 0, right? That one's an easy one. That one's pretty straightforward. What about, let's look at quadratic functions. So here we have f of x equals a2x squared plus a1x plus a naught, right? And so to find the intercepts for this one, we need a2x squared plus a1x plus a naught equal to 0. This is less easy, right? This is a less easy problem to solve, but it's not unsolvable. I think we should go ahead and do it. You might know the answer to this. The quadratic formula is pretty famous, but let's go ahead and go through the exercise of finding that result, right? It's not a bad thing to know how to do. So if I wanted to solve this, we'll use a method of completing the square, but we're going to do a little bit of work first. I'm going to divide everything by a2. Remember, a2 is not 0, so this is a perfectly reasonable thing to do. So I'll have and let's subtract that constant term at the end to the other side. And now I'm going to add the same thing to both sides. What I'm going to add is half of the coefficient of x and then square it. So if I take half of this, I'll get a1 over 2 a2, right? If I double the denominator, I make the fraction half as large, and then I'm going to square it. And I can do the same thing over here. I have to do the same thing over here, I should say, because I can't just add something to one side. Since we have a nice equation, I can add the same thing to both sides. On the left, the reason I did that is because what's right in the name, I was completing the square. I can now factor this as x squared plus a1 over 2 a2. Over here, let's do a little bit of work. Well, let's go, I'll do it a step at a time. A naught over a2 plus a1 squared over 4 a2 squared. Let's continue to work on that right-hand side for a moment. So I want a common denominator. And I see that we've got an a2 and a 4a2 squared. So if I multiply that first one by 4a2, I'll get minus 4 a2 a naught over 4 a2 squared plus a1 squared over 4 a2 squared. And I have a common denominator now, so I can write it as one fraction. I'm going to write it in a little more familiar of a way. We've got a1 squared minus 4 a naught a2 all over 4 a2 squared. Okay. Meanwhile, nothing's changed over here. Remember, our goal here is we're trying to find the x that satisfied this first equation. We've done some manipulation. I want to get to that x, right? I'm closing in on it because the problem in the beginning, we have two x's. Now I've got one x. Oops, I have a mistake here. This is not squared anymore. That was the whole point of factoring this, so it's not squared when we factored it. Now we'll take the square root of both sides. So I get x plus a1 over 2a2. I'm going to take the square root of this side. I have a1 squared minus 4a0 a2 over 4a2 squared. I need plus or minus, right? There's two possible solutions. If we have something squared equals 9, the thing that was squared is either 3 or -3. So we have to account for both of those. And then I'm going to subtract what's next to the x to get x equals negative a1 over 2a2 plus or minus this whole thing. So let's do some work on this. There's not much we can do to the top, but the rules of exponents, which are also the rules of radicals, tells me I can do this, which means that that denominator is just 2a2, right? And then we notice, just scroll this, oh, come on, there we go. Then we just combine those two terms and we get our solutions. X is equal to negative a1 plus or minus the square root of a1 squared minus 4a0 a2 over 2a2, right? That is the quadratic formula, right? It's a little exercise in algebra, but it's nice to know we can do it, that we can always find solutions to this equation, provided, right, this thing in the radical is positive. When it's not, it means there are no solutions there. Not every parabola has this intercept, right? You can easily imagine the picture. If I have a parabola right there, and I'm looking for where it intersects the x-axis, it's not going to, right? And so then we'll find out there's a negative in the radical. We know we can't find that solution unless we're using complex numbers, which we are not. Right, okay, so just in case this is a little too unfamiliar, this is exactly the same thing. If we relabel our, what you're probably more used to seeing is ax squared plus bx plus c equals 0. If we solve that equation, we do the exact same things. It's just relabeling this. We get our solutions as negative b plus or minus b squared minus 4ac all over 2a, right? Which is the same formula, just I'm calling a, a2, b, a1, and c, a0, and everything. Everything is in the same place there, just written with different labels. Okay, and so that gives us the solution, right? So we can always use this quadratic formula to find solutions, to find the zeros of our quadratics. So let's go ahead and do that. Let's look at, actually, let's hold off on doing that. Let's first look at this function. So here's a quadratic, g of x equals 6x squared minus 5x plus 2. We don't always have to defer to this quadratic formula. In this case, for instance, I might be able to factor this thing, right? Well, I know I've got factors of 2 and 1. I know they both have to be negative. That middle term's negative and it's positive, so they both have to be negative. I need to get a negative 5x, so it looks like, and we're going to have factors of 3 and 2. So it looks like we'll have 3x and x. Double check, I get, oops. No, that's not right. It should be, oh, Oh, that was right. 2x, sorry, let's just double check. 6x squared, we get minus sorry about that. I know there's a little glitch there. I realized I miscopied this when I started it and I had the factoring in my head. So let me write down the problem that should have been here. Sorry about that. There was a reason it wasn't working out the way I thought it was supposed to. So here's our nice factoring of this. We get minus 6x squared minus 3x minus 4x plus 2 gives us 0. And then we know the only way two things can multiply to be 0 is if one of them is 0. So one of these two things has to be true. And we get 3x equals 2, or x equals 2/3, or x equals 1/2, right? So there's our two solutions. Let's use the quadratic formula to do the same problem. So so this factoring works, there's nothing wrong with this, but we also have the option, it's nice to see that they will both give the same results. We can also look and see that x is going to be equal to negative. So in this construction, there's our b. So negative b would be 7 plus or minus b squared. So 49 minus 4 times 6 times 2 over 2a, and a, so over 12. All right. And so if we work this out, we get 7 plus or minus. So what do we have? 49 minus 4 times 6 is 24, times 2 is 48. 49 minus 48 is 1. So this is 7 plus or minus 1 over 12. So when it's plus, we get 8 over 12. When it's minus, it's 6 over 12, which is, of course, 2/3 and 1/2. So they both give us, as they should, the same result. Right? So let's turn this off for now. What's this good for? Well, we're interested in zeros for a lot of reasons. One reason that we'll use right now is we can graph with the zeros. So here's a quick sketch. Here's my two zeros. I'm going to call this 1/2. 2/3 might be somewhere over here. And so I know, actually, this is fine. I know this is a parabola. I missed, but it's facing up. Let's do that again. It's a parabola facing up. That goes through those 2 points, right? If this is 1/2, 0, and this is 2/3, 0, right? It gives us a quick idea of the graph. There's lots of reasons that we'll see as we move forward why we might be interested in the zeros and understand the behavior of these functions. One other thing to note with this, I know my picture is not perfect, but it's pretty easy, I think, to imagine that this graph is symmetric, that if we drew a line down the middle of the graph, again, pretending my picture is perfect, the vertex would be right in between those two roots, right? And this is, in fact, the case. Remember, the roots are given by negative b plus or minus b squared minus 4ac. I can rewrite this as negative b over 2a plus or minus b squared minus 4ac over 2a. Look at this equation closely. Forget how complicated this is. This is some number, okay? So we've got negative b plus or minus some number, the same number, right? Which means those roots, if we start at negative b over 2a, those roots are going to be some distance on one side and some distance on the other. And so the number negative b over 2a is the number right in between those two roots. And if you recall in the last video where we looked at quadratics, this is our formula for the x-coordinate of the vertex it shows up right in the quadratic formula there. It's the number in the middle that we add and subtract the same thing to, and it's going to be aligned with, it's going to be the x value of that vertex. Okay. All right. Let's do one more example of finding roots, and then finish up. So we have this nice quadratic formula, right, for degree 2 polynomials. There's a formula for degree 3 and 4. They get really complicated, and so I certainly don't know them off the top of my head, and have not found them useful enough to know often. And so when we want to find roots of higher powered things, we have to hope. There's a lot of tricks out there, and we're not going to go through all of them. I'm just going to do one example here and then say some more about it. So for instance, negative x cubed plus 6x squared minus 9x, right? So here's a cubic, and suppose I wanted to find the roots of this thing. So I would be looking to solve this equation. So I would probably, well, let's factor out a negative x from everything. It leaves me x squared minus 6x plus 9. Then I can factor this minus 3, x minus 3, or negative x times x minus 3 squared equals 0. And this gives me two possible solutions, either negative x equals 0 or x minus 3 squared equals 0. All right, so this, of course, is solved if x equals 0. This is solved if x equals 3. So let's try to graph with this information. Let's just do a quick sketch. So there's a quick set of axes. Here's x equals 0. I'll just put x equals 3 out here. So let's combine some of the information we know to get this sketch. So first of all, let's go back to the original. We've got a cubic with a negative leading coefficient. So remember our pictures from before, right? A cubic typically looks like this when that leading coefficient is positive. So we've got negative, it's going to be looking like this, right? So I know that off in this direction, it's going positive, and in this direction, it's going negative, right? So now we have an interesting question. How do we go through these 2 points and end up this way, right? And I can't connect these with a flat line. Well, what it turns out, this is a nice little feature. And this is another one I'm not going to go through with too much explanation other than to say this. Near a 0, the factor, just like when we go very far away from 0, the thing that matters the most is this leading coefficient, or this leading term. That's what we used up here. Near a 0, the thing that matters the most is the factor that gave us that 0. So here's a root, a 0 at x equals 0, right? We call these intercepts roots sometimes. This is the factor that led us there. If we think about x as a function or negative x, it's a line. And what that tells me is I'm going to go through this root like a line. Here, at x equals 3, the factor is like a parabola. And that tells me I'm going to hit that root like a parabola. I'm going to have a little, I'm going to just touch it and continue going negative after that root, okay? So it helps us get a good, having these factors and these zeros helps us, and then combining that with the end behavior gives us a nice picture of these functions. Let's compare it to a graph on Desmos. Right, so obviously this is a much nicer picture. but we got the essential shape correct, okay? And there's another obvious question here, which is, why in the world would we want to spend time graphing when we've got nice programs like this and we've got them in our pockets at all times? And I've said this in other videos, I'm going to continue to say it over and over again. It's still a valuable exercise, right? If I'm looking at this polynomial, I'm probably not sketching a graph because I've sketched 100 of these graphs, but I can quickly picture what we got here in my head. And so the more familiar we get with functions, so that we can do these kinds of things, and the only way we get familiar is through this process, right? Looking at the pictures not nearly as much as picking it apart by hand and discovering how it works and behaves, right? That's how we can make intuitive leaps, right? Pretty soon, we're going to be taking things like cubic polynomials and using them as part of a much larger problem. And if you don't have a good understanding, a good handle, right? If you don't recognize like, oh, there's a negative in front, I can already kind of picture how it's going to be. I see a couple of factors. All right, I kind of got a handle on this thing. You're not going to be able to work with it nearly as easily. So that's a good enough reason to go through these exercises. There's other things too. It's always good to practice our algebra skills, get better at manipulating equations, right? All these skills, the more solid they are, the better off we're going to be when we move on to the more complicated things. One other thing to notice, and then I really will finish this one. After degree 4 polynomials, there is no guaranteed formula for finding these roots, right? In certain cases, right, we can find them, like the simple case y equals x to the 5th. There's degree 5, of course I can find those roots, right? And so there's other ones like this where you might have some nice, easy ability to factor it or something like that. But in general, we don't have a method to find the roots, and in fact can't. There's going to be no algebraic manipulation that will give you the roots. And we're stuck with approximations, incredibly good approximations. And remember, these are meant to be a review as we move into calculus. The idea of approximating turns out to be very important in calculus. And at least for me, when I was in mathematics, this took me a while hard to get used to and appreciate. I thought of math as this beautiful thing where everything had finely tuned answers. It does sometimes, but it's also really good at saying, hey, here's a place we can't get answers. What's an amazing approximation that we can get? And we're going to start looking at methods and use calculus to do some amazing approximations of things, which turns out to be good enough to do things like have the satellites we have in space right now that do so much for us in our lives. Okay, anyways, I will really stop there. Thanks, everybody. I will see you in the next one.